Welcome again. Today we are here to discuss the fine grain analysis. Fine grain analysis or sedimentation method of analysis concerning which category of soil solid for silt and clay, that is fine soils. And what is the size range? Less than 75 micron general. Okay, so as I have said in previous session that it is of two types: pipette method and hydrometer method. We will study this in very detailed. Hydrometer method. But prior to going through pipette and hydrometer method, we must understand the basic idea behind sedimentation method. So for general, make a note that the entire sedimentation, this portion is very important because now which I will discuss in this session will relate three subjects: fluid mechanics, environmental engineering and soil mechanics. So the entire sedimentation process is governed by a famous law. Okay, it is the name which I am going to write now is a famous, very famous scientist. He was governed by Stokes law. So the first basic to start the sedimentation analysis is to understand what is Stokes law. So let us try to understand Stokes law and then continue with pipette and hydrometer. So Stokes law, what is it? Stokes law. According to, I am writing the statement of law. According to this law, if a solid particle, spherical, in shape, falls through an infinite medium of fluid system, then it achieves a constant terminal velocity called settling velocity, Vs. So as we made this statement here, so let's look into this statement. What is this statement? What this statement says? Let us start with a diagram to understand this. So let this be the infinite medium I'm drawing here. It is infinite. There is no starting and there is no ending. And it is a fluid system. It is a fluid medium. Just a please wait. It will be better representation. So let this be the infinite system of fluid, and in this system there is a spherical solid particle. Okay, let this be the starting position of this spherical solid. Now after falling continuously it achieved, let this is the position here which that spherical solid have. So what is this? This is spherical solid particle. So if this is the condition, then this soil solid will attain a constant velocity Vs, which will be called as Vs, and what it is settling velocity. Okay, and this will be constant, that is Vs is constant velocity as terminal velocity. This is constant velocity is which is achieved at long time when the particle continuously fall into the system of infinite system of fluid. So this is the Vs. Now as we know the basic concept that what are the let's look into what are the forces that were acting over this fluid, no, not over the fluid, over this spherical soil solid. Let it be any spherical particle, any solid. So what are the forces which are acting? First of all, it's the weight which is directed from this Cg, let this be the Cg, in downward direction, the weight of that solid. Another force, it is a very famous force given by Archimedes, is Fb, buoyancy force, which will be always act in upward direction. Okay, if weight acts in downward, then it will always act in upward direction. Now another very important force which is acting here is which force? Drag. Okay, Fd, drag force. There are three forces which are acting. Now let us try to understand the logic. Let us try to make equilibrium of these forces. According to Newton, we all know that F equals m times A. What is this A? This is acceleration. A is acceleration. So we also know that in differential form, acceleration A is defined as derivative of V, difference between the velocity at two positions, two velocities, over difference in time. This is the basic definition of acceleration. So as velocity we have said at as I will write in differential form, I will make the limits. Okay, as A equals limit t tends to infinity dv over dt tends to 0 at infinite time. This is the correct representation. So we all know that if a differential is constant is 0, it means dV is constant, which means V1 minus V2 is equals 0. It further, if we make the simplification, then we will come to know that V1 equals V2, that is no change in the velocity with respect to time. Hence, there is no acceleration in the solid. Hence, A tends to 0, which further means that F force net in the direction of movement m times 0 equals 0. So, look at this system and try to make equilibrium of forces in the direction of movement. Okay, how we can write? Weight is acting in downward direction plus drag, sorry, it will go in other side of the equilibrium. So hence at equilibrium condition, state weight must equal to buoyant force plus drag over surface of the solid grain, drag force. We all know what is volume of a sphere, pi by 6 dq. I have previously cleared the idea of unit weight, so let gamma is the unit weight which whose unit goes like kilonewton per meter cube. So what will be the weight of solid grain which is falling here? Will be gamma solid times the volume, pi by 6 dq. Yes or not? Will be this much kilonewton, let it be. So what is buoyancy force? Buoyancy force equals the volume of displaced liquid, displaced fluid multiplied by unit weight of concerning fluid medium. In this case we assume water medium. So what is the volume of displaced liquid? Volume of displaced liquid, V displaced equal to volume of the solid grain. Yes or not? This is the same amount of same volume which the water get displaced, volume of solid particle. So what we get? The expression for buoyancy force, Fb equals pi by 6, again it is also pi by 6 dq multiplied by gamma w, unit weight of water. This is the second formula. Now we will try to understand what is drag. F drag, what is this, how it is defined? Look, drag force is defined as, actually this concept arises from the boundary layers. Okay, boundary layer theory. Boundary layer theory, if you will study in fluid mechanics. So just for a note, I am making that derivation, that how it is derived. Please try to understand. So let this be any surface which is placed, okay, and over this surface there is a fluid flow, okay, a fluid is flowing, this is fluid flow, and this is the thickness of delta, thickness of boundary layer. For now, by this term, the for base clear understanding, prefer fluid mechanics. So this is thickness of boundary layer, and let this be velocity, free mean velocity, that uniform velocity. This is fluid flow, fluid flow with uniform velocity. So now as the fluid flow continues over the surface, as just they come in contact with a surface, then the velocity of the just bottom layer of the fluid which is in contact to surface goes zero, as this surface is in static condition, static condition, static condition. So there, by application of no slip condition, which are the equilibrium condition of fluid mechanics, no slip condition, the velocity of this layer, the bottommost layer, tends to zero with respect to the surface. Similarly, the velocity get reduced in both directions, that is x and y, and as a result we get this form of layer, and above this layer the velocity is approximately equal to 99% of u infinity, okay, above this layer. So the layer below which the fluid is moving with velocity lesser than 99% of free mean velocity is the boundary layer thickness. So why this is occurring? This is occurring because there is a force acting in opposite direction called shear stress. Shear stress is acting, hence the velocity is reduced in x direction, x direction. So there is a term called CD, coefficient of efficient of drag, okay, and how it is defined is, CD is defined as shear stress over x length and unit width of surface. This is average shear stress divided over dynamic kinetic energy. What is, kinetic energy, Ke equal to half time mv square. So the dynamic kinetic energy is, and this is per unit volume now, This is per unit volume. Yes or not? So dynamic kinetic energy is kinetic energy per unit volume. So by making equilibrium of this, we get an equation for drag force as F drag equals half mv square times cd, okay, into area of plate. Okay, this is the drag force which is acting. Okay, we have seen this is the F drag. Now make a correction here. As I have said, the dynamic velocity or velocity of energy or the kinetic energy per unit volume, Ke dynamic. As I have said that it is equals to half time mv square over volume. Now if you will expand, you know what is m? M we can be written as rho, liquid. Here water is liquid, times volume into v square over volume. So Ke dynamic finally can be written as half times rho w into v square. It can be written as in this fashion. Hence Fd finally it can be written as half rho w into v square, and this is vs, actually settling velocity, times c coefficient of drag into area. Okay, this is the drag force. And what is this area? This area is the exposed area or the surface area. Okay, this is surface area. Now means for a spherical solid, what will be the exposed surface area? This is spherical, so the exposed surface area means area which is projected in vertical plane and area which is projected in horizontal plane. This will be circular in shape or not, of the same dia D, which is of the solid of dia D. This is circular. Both the exposed surface will be circular. D circular. So what is this area? Pi by 4 times D square equal to area. Here this area which we are going to use, this area, because the drag is acting over this area only. Drag is acting Fd over this area. Hence, let now we make equilibrium. What we got? Weight. Weight equals Fb plus Fd. So it is equals rho solid, okay, times g, acceleration due to gravity, into pi by 6 dq equals rho w times g into pi by 6 dq plus half times cd into rho w into vs square into pi by 4 d square. So this is the equation, final equation which we have, and on simplifying this equation we will come at a generalized equation which is being used for settling velocity, because we finally need to deduct the what is settling velocity Vs from that equation, which goes like g minus 1. If you will simplify that above equation, you will get this equation, gamma w times d square over 18 nu. You will get this equilibrium equation. What is new here? I have not told about this. This is dynamic viscosity. From where does it came? It came from the CD. CD goes like 24 over RE in case Stokes, for Stokes law validity. Okay. From here we get the Newton. What is RE? RE equal to Reynolds number which goes like rho into V into D times dynamic viscosity, coefficient of dynamic viscosity, rho V D over nu. This is characteristic dimension. So finally we derived the equation for settling velocity. Make a note that nu for water at 20 degrees centigrade is equals 1 poise, 1 centipoise. What is poise? The unit of nu is unit of nu. If you will find out, from unit of nu is computed using Newton's law of viscosity, which is tau equal to tau equals nu into du over dy. This is velocity difference, this is shear stress. Newton's law, this is Newton's law of viscosity. From this law, if you will try to compute the unit of nu, it will come as Pascal second, which is equals to, Pascal is the pressure, Pascal is the unit of pressure, which is force per unit area. Okay, kilonewton per meter square times second. This is Pascal second, which is unit of viscosity. This is called Pascal second, and 1 by 10 Pascal second equals 1 poise. Okay, this is in centigrade system. So, and then what will be 1 centipoise? So 1 centipoise will be 10 to the power minus 2 poise. Yes or not? So this is unit of viscosity. This is all about viscosity, dynamic viscosity. Then there is another viscosity, okay, kinematic viscosity coefficient, which is just simply the dynamic viscosity is divided over the density, is termed as kinematic viscosity. So this is the viscosity of water at, so mu water at 20 degrees centigrade. The basic cause for viscosity is, cause for viscosity is cohesion. So now as temperature decreases, viscosity decreases because cohesion decreases. So let's move to our topic where we are in sedimentation analysis. So this is all about Stokes law, how Stokes law goes. So G for inorganic soil solid approximately ranges from 2.65, let us take as 2.65 for inorganic soil solid grain. So how Vs can be written as 2.65 minus 1 G minus 1 times 9810 into D square over 18 times 0.001. Yes or not? This is dynamic viscosity of water. Now if you will simplify this equation, you will get a final result which is approximately equal to 0.899 D square meter per second, okay, or finally it can be written as 0.9 D square meter per second. This is settling velocity Vs, validate under Stokes law. It is only for Stokes law applicability. And here the diameter of particle used is in mm, unit is mm, okay. So here because cohesion, so as temperature increases, C decreases, so mu decreases, okay. So this is all about Stokes law. Now let us try to understand that how the Stokes law are applicable in sedimentation analysis of the fine grained soils. What are its drawbacks and what are its advantages and what are limitations of Stokes law? So we will start with limitations of Stokes law in sedimentation. Note these limitation which I will discuss now is only under sedimentation analysis in soil. Sedimentation analysis. So limitations. The first limitation is that Stokes law said that the soil solid or the solid particle should be spherical in shape. Okay, but in actual what happens? Is it truly spherical? The solid grains which we are, the fine soil, their grains are truly not spherical. They are somewhat flaky in nature. So the first limitation goes like, according to Stokes, the solid should be spherical in shape but in actual the grains are not spherical, it is somewhat flaky in nature. What is flaky? Flaky means too much thin. Okay, thinness. Flaky means thinness. There are two classes, flaky and elongated. Elongated means too long, flaky means too thin. This concept will come under aggregate sections. Okay, when we will discuss the aggregates, in case of building material, when you study there or in highway also, you will come across these terms, flaky and elongated. So let's move towards second assumption. Second assumption is, according to Stokes law, what Stokes said, the fluid system in which the solid is falling should be infinite. But in sedimentation jar, is the sedimentation jar can be considered as infinite medium? No, it has fixed dimensions. You know the dimensions of a sedimentation jar. So it cannot be considered as infinite medium. But the Stokes law is applicable in case of sedimentation jar because the jar is of some volume, but the fine solid which are falling in the jar are very low size, which are less than 75 microns. So for them the jar can be considered as infinite medium. Okay, but it is a limitation. So what is it? According to Stokes, the fluid medium should be of infinite dimensions. Okay, but the sedimentation jar is of fixed dimension. Now let us move towards the third limitation. The third limitation is, Stokes said Stokes law is only valid, only mention this, only valid for type 1 or discrete settling of solid, but in sedimentation jar settling is not of type 1 always. Now I think I should discuss something, just that what is type 1 or discrete settling. Discrete settling means individual particle settling, okay, that must be individual settling, individual type of settling of particle. What does it mean is, look, what does it mean, that let this be the jar, sedimentation jar, another sedimentation jar, and filled with fluid, and these are the sedimentation jar and filled with fluid. Okay, so here let be the grains. So if settling is such that they settle individually, that there is no any collision between individual particle, then this is type 1. Or discrete, they settle individually, they settle of their own. Okay, this is type 1. But if in another case, if you will consider, if the settling occur initiated, then while settling, the particle, the settling zone of individual particle become closer, they settle combiningly. This type of settling are called as type 2 or type 3 settling. There are different type of settling: compression settling, okay, compression settling, it may be compression settling. So this type of settling is generally seen in jar. Okay, but Stokes is valid for this, hence this is a limitation for Stokes law. Okay, now let us look into the fourth assumption or the last assumption which has been made considering Stokes, which goes like, the fourth assumption is that it is a very pure technical term of fluid mechanics actually. Okay, the fourth assumption. So according to this assumption, Stokes law is only valid, make a note, only valid if flow around the solid is laminar. Okay, if flow around the solid which is falling in the infinite medium is laminar, then the Stokes law is valid. But in actual it is not laminar. There is another point regarding this which goes like, laminar flow can be maintained if the size of particles ranges between 0.2 micron to 200 micron. So this is the range of particle size in under which Stokes law is valid. So it should be remembered anyhow. This is the range under which Stokes law is valid. So what happens if this particle size is not maintained? So if D greater than 200 micron, in this case Vs not remain constant, there is a acceleration, gravity acts and settling velocity, we do not get a settling velocity, hence Stokes law is not applicable. Also if D is less than 0.2 micron, what happens under this situation? Under this situation there is no type 1 settling, there occurs another type of settling which is called Brownian motion. or zigzag. They fall in zigzag pattern. Okay, settling occurs in zigzag pattern. Zigzag. So for this type of particles which is following the Brownian motion, there are other methods. Okay, other methods for finding out particle size classification. There are also methods for those soils also. Very fine soils, very fine. So as I have said that Stokes law is valid only for condition when the flow around the falling solid particle is laminar, and Stokes also provided a range that laminar flow around the falling particle can be maintained if the dia size of the particle ranges between 0.2 micron, that is 0.2 into 10 to the power minus 3 mm, to 200 micron, that is 200 into 10 to the power minus 3, which equals 0.2 mm. Okay, so Stokes law is not applicable if size smaller than this and greater than this. If size is greater than this, I have said settling velocity does not remain constant as there is acceleration of this solid. And if size lesser than this, then there is the Stokes law is not applicable because the flow doesn't remain laminar. Under this section, this for 0.2 micron, less than 0.2 micron, Brownian motion occurs. Brownian motion or zigzag motion, zigzag settling occur. Zigzag settling occur. So how to find the percentage finer for this type of soils? There are also method available for analysis of this type of soil. The very first method is X-ray diffraction method. Just remember for objectives, X-ray diffraction. No need to go deep into this method. Diffraction method. And the second method is electron microscope. We use electron microscope, electronics microscope. I guess everyone seen one during the college times in botany lab or zoology labs. Electron microscope method. Well, thank you. This here we end up with the limitations of Stokes law to the sedimentation analysis. Now in very next lecture we will continue, as this lecture has been already gone lengthy. So in next section we will continue with the procedure of sedimentation analysis, and we will look at least one of the method, pipette or hydrometer. Thank you. Thank you for observing.